Okay, so let's start talking about our first of our three types of bonds a little bit more in depth here. So we're going to focus on our metallic bonds, our metallic bonding. We just did an intro to chemical bonding lesson and we did some colors, right, you guys? If you'll remember that our metallic bonds here, which were metals, we colored red. So what we're actually going to do is we are going to color the title of our notes page, which says metallic bonding. We're going to color that red. So that way when we're studying and flipping through our notes pages, we get to this page and we remind ourselves that everything on this page is all about metals and metals only. To remind yourself, you guys, oh my gosh, there is a lot of metals on this periodic table. Like most of the elements are actually metals. So there's a lot of options here for what types of things can undergo metallic bonding. So I'm now excited to learn a little bit more about metallic bonds. So I think I alluded to last time in our intro lesson that a term for metallic bonding is the sea of electrons. So look at this, you guys. I bet you this is a bunch of metal cations swimming in their sea of electrons. Very, very fun. Okay, so metals, that's what metallic bonding is. A metal is an element that readily forms cations, which are positive, and therefore can make metallic bonds. Almost 80% of the elements on the periodic table, you guys, are metals. Everything that we colored there red is a metal. Here's some examples. We got chromium, gold, lead, silver, magnesium, tin, zinc, titanium, nickel. All of these, right? So anything that I've colored red is a metal and will form a positive cation and can therefore make metallic bonds. Okay, so for each one of our bond types, we're going to have a section that says what happens. We're going to have a section that says what is the attraction. We're going to have a section that is what is the structure. We're going to have a section that gives you examples. And then we'll have a section that asks what the relative strength of each bond type is. Then we're going to have a bigger, longer section describing how all of this stuff creates the special properties of that unique type of bond. So I like consistency and groundedness here when we talk about the three types of bonds. So breaking it up into these distinct sections, I think will make it a lot easier for all of us to kind of not lose track of what the different bond types are. Anyway, that was a huge tangent. So what happens in a metallic bonding? In a group of metal atoms, all atoms collectively lose their valence electrons and become positive. Through this, they achieve a stable octet. These delocalized electrons can drift freely from one part of the metal to another. And I think I mentioned in our first video that, y'all, it's kind of like little kids swimming around in a ball pit where the balls are the valence electrons and the kids are the metal cations. It is a very fluid structure. Okay. What is the attraction of metallic bonding? We kind of mentioned this in our intro lesson, but metallic bonding is the electrostatic attraction between metal cations, positive, and the delocalized electrons, which are negative. I had us write those two pieces in red because it really highlights that electrostatic means positive and negative attraction. I've also made you guys write what the positive piece of attraction is. It is a cation. And what the negative piece of attraction is. That's the electrons that have been delocalized into the sea around it. So this positive to negative electrostatic attraction is the bond that holds metal atoms together. Okay, our next section is what is the structure? So we know what happens. Electrons are delocalized, and we know that that leads to an electrostatic attraction. But then how does this create a structure of some sort? So the structure of metallic bonding is called the sea of electrons. And I thought I'd show you guys a really, really cute, fun, quick video kind of visualizing this sea of electrons and how it's created. Okay, I know there's no sound in that video, but it does a great job of visualizing that those valence electrons are delocalized from each one of the atoms and move. You can really see the movement there in that sea of electrons. I feel like I show you guys like a lot of really old looking videos, and promise I've like tried to find like better ones that are updated and look, you know, more for the times. But I find like a lot of the old videos actually do like a really good job, so that's why I'm keeping them in there. All right. So here we go, examples of metallic bonding. Y'all, we just call them whatever the metal they are, okay? Sodium is a metal. So a sample of metallic bonding with sodium would be called sodium. Magnesium is a metal. So a sample of metallic bonding with magnesium would just be called magnesium. Aluminum, copper, zinc, lead, y'all, any element to the left of the staircase is a metal, and therefore a pure sample of that metal will be held together by metallic bonds. One thing I'd like for you guys to notice, sodium. If I look at sodium on my periodic table, he's in group 1 with all the alkali metals. And we do know that sodium in the alkali metals have one valence electron. Well, if metallic bonding, they delocalize their valence electron, each one of these sodium atoms will delocalize only one. And each one of these sodium atoms will then form a cation with a +1 charge. Okay, that makes sense. Zipping on over here to magnesium, he's in group 2. That means he's going to delocalize 2 electrons, and he will form an ion with a +2 charge. That's why you see 2 pluses. Aluminum, group 13, he's +3. Loses those 3 valence electrons. So here's the trick, is depending on what type of metal you are on your periodic table location, you're going to lose different amounts of electrons, and you're going to have a different strength charged nucleus. I bet that maybe creates some of the variety in the different strengths of my metals depending on what they are. And you would probably be right with that. We would assume that aluminum is a little bit stronger than something like a sodium sample. Okay, probably because I have a lot of negative charges and a lot of positive charges. That leads to a much stronger electrostatic attraction. Okay. So like I said, there's a lot of variation in the strength of metallic bonds, mostly because the number of delocalized electrons varies depending on what metal cations are involved. More delocalized electrons means stronger bonding. So compared to ionic and covalent bonds, metallic bonds have the weakest bonds. So this is the relative strength of metallic bonding. I think in our intro lesson, we wrote at the very bottom the relative strengths, and yes, y'all, the metallic bonds, if I were to overall compare them, which there is some variety within different types of metals, but if I were to overall compare them, the metallic bonding type is the weakest of the bond types. So how does this all lead to the different properties of metallic bonding? How does melting point and how does boiling point, how are they affected? Melting point for metallic bonds or metals is high. Boiling point is high. When I say a melting point is high, a melting point is the temperature at which something goes from a solid to a liquid. My states of matter, we know my solids are packed in tight. They are still moving, vibrating in a fixed position, but they're packed in tight. They have a defined volume and a defined shape. To turn into a liquid or to melt, the atoms must be able to move around each other, right? So a melting point is the temperature at which that solid is able to turn into a liquid. So when I say a melting point is high, that means this is going to require a lot of or a very high amount of energy or a high temperature for it to turn from a solid to a liquid. Its melting point is a high number on the thermometer. Same thing with boiling point. Its boiling point is high. That means it's going to take a really high temperature for once it is a liquid to then turn into a gas. Okay, so how come these melting points are high and how come the boiling points are high in my metals? To melt or to boil, atoms, they've got to be able to move and separate. Overcoming that strong electrostatic attraction between those positive cations and the negative delocalized electrons require a lot of energy. You were like, wait a minute, I thought she said we are in a sea. That sounds amazing to me. Yeah, they're in a sea, but they're going to be close together because those positive and negatives are still going to want to be in close proximity to each other. Okay, so here's some examples of some metals for metallic bonding, and these melting points are crazy high. Guys, this is not in Fahrenheit. To give you an example, like normal temperature, like room temperature in Celsius would be like 25 degrees. So when I'm seeing these 180 degrees, I am not thinking 180 degrees Fahrenheit. I'm thinking something much higher than that. Okay. So, and as we mentioned before, oh, this is really cool. So lithium's in group 1, he only has 1 valence electron. So his is kind of relatively lower than some of the other ones, which may have more valence electrons to lose. And y'all, boiling point is even higher. That makes sense. Melting is going from solid to a liquid. Boiling is going from that liquid to a solid. I need to have turned into a liquid before I'm allowed to boil. So yes, those boiling points are always going to be higher than my melting points. But both of these, y'all, they look real high. Down here, there's a little blip at the bottom that says for transition metals, the D block. The D electrons are also delocalized in metallic bonding. So then the more delocalized electrons from those transition metals, the harder and the stronger the metal. That is why we see our transition block metals, the kind of more, I guess in the simplest terms, metal-like, where you're like, yeah, that's a hard sample of copper. Yeah, that's because they are able to delocalize their D electrons too, not just their valence, which means more electrons, stronger bond. Anyway, so the main takeaway from this is my metals, they got high melting points and high boiling points. That is why you do not frequently see like liquid metals floating around here at room temperature, unless you're mercury. Mercury is actually a liquid at room temperature, which is pretty cool. So more properties of metals. High luster. You guys, that means they are shiny. Yes. High density. Oh gosh, here she goes with the density again. Density is mass per volume. So if you have high density, that just means your atoms are tightly packed together in a small amount of space. Yes. And then the state of matter that metals are most commonly found in, they're usually solids at room temperature. Okay. Some more properties of metals. These are the real important ones that I'm going to want you guys to know across the board for all of my 3 bond types. Conductivity. So metals are good conductors of heat and electricity. Let's talk about this. I bet you have put a metal pan on the stove and it has gotten hot real quick. That's because heat is allowed to conduct through a metal sample very quickly and very easily. So I like this picture down here, you guys. This picture is showing those yellow metal cations, and the little blue things are the electrons. And the reason why heat can transfer through a sample of metals very quickly is because those mobile electrons, they can move, you guys. So when they get excited and start moving, we know that particles of matter, when they get heated up, they start moving. That transfer of heat energy is able to very quickly move through there because of that fluid environment, okay? So we're transferring heat really, really good here. It's a good conductor of heat. It's also a good conductor of electricity. So electricity is literally an electrical charge, which is made by electrons. Well, why would maybe a sea of electrons be good for transferring electricity? Y'all, we got literal mobile electrons in this sea here. So these mobile electrons can flow freely and help transfer that heat and that electrical charge. That is why we have copper wires to conduct electricity, you guys. These metals are great at that. So yes, metals are good conductors, and they are good conductors at all states. I don't care if it is a solid sample. I do not care if it is a liquid sample. I do not care if it is a gas sample. That would be on another planet, I believe, but they're all going to be great conductors of heat and electricity in all states of matter. More properties. Here's some terms. Oh, these terms. Ductile is a term that means you can draw it out into a wire. I mentioned copper wire before. I can do that with metals really actually quite easily, even though metals are real strong. Okay, the reason why is that, y'all, the cations can slide easily past each other because of this C electrons allows for more fluidity, right? So here's a little picture. It's showing that, ooh, I can draw it and slide it. Our other term is malleable. That means they can be hammered into flat sheets. So looking at this situation over here, I have some samples and some sheets of metals. I can do that quite easily for the same reason. The cations can slide and spread past each other because of that really fluid sea of electrons environment. Very cool. Ductile is wires, malleable is sheets. Love that for us. Okay, the last thing not last thing, we got alloys to talk about after this, but I love this video. It's a little bit longer of a video. I do want us to take the time to watch it right now because this bonding concept is very much better learned through looking at visuals and kind of summarizing things as we go on. So we're going to watch this little summary video of metallic bonding and some of the special properties of metals.
In previous videos, we've explored 2 types of bonding that occur between atoms. We've looked at ionic bonding, which occurs between a metal and a non-metal element, and involves the transfer of electrons between atoms to form oppositely charged ions. And we've also looked at covalent bonding, which occurs between non-metal elements and involves the sharing of electrons between atoms to form molecules. In this video, we explore a third type of atomic bonding, called metallic bonding. This is the bonding that occurs between the atoms of a metal element. As we'll see, this bonding involves the free or delocalized outer electrons of the metal atoms and the attraction they have for the positive nuclei. So, let's take a close-up look at metallic bonding. Zooming up millions of times on this aluminium metal, we see the aluminium atoms packed tightly together in a regular lattice. To understand the atomic bonding that holds this lattice together, we need to consider the electron arrangement of the metal atoms. Aluminium atoms, with 13 protons and 13 electrons, have 3 outer or valence electrons. Metals have only a weak hold on their valence electrons, and as a result, they become detached from the atom and move freely throughout the structure. This leaves the remaining core of each aluminium atom with a positive 3 charge. The free or delocalized electrons create a sea of electrons surrounding the positive cores of the metal atoms. This sea of negatively charged electrons is strongly attracted to all the nearby positive metal cores, and we call this attraction metallic bonding. It's this strong electrostatic attraction that holds the atoms together in the lattice, and it's the reason why metals have similar physical properties, like being shiny, malleable, and electrically conducting. The melting points of different metals vary widely. Metals with higher melting points have stronger metallic bonds. Sodium metal only needs to reach 98 degrees Celsius to overcome the metallic bonds sufficiently to enter the liquid phase, while magnesium, with stronger metallic bonding, needs to reach 650 degrees Celsius to overcome its metallic bonds. The difference in the strength of the metallic bonds depends on several factors. Sodium, a group 1 element, has atoms with 1 outer electron. The outer electron of each sodium atom becomes delocalized in the lattice to give sodium atom cores with a 1+ charge. The metallic bonding that results is the attraction between these free electrons and the 1+ charge of the atom's cores. Magnesium is a group 2 element, so each atom has 2 outer electrons. The outer electrons of each magnesium atom become delocalized in the lattice to give magnesium atom cores with a 2+ charge. The metallic bonding that results is the attraction between these free electrons and the 2+ charge of the atom's cores. With 2 electrons per atom, this sea of electrons has twice the density as that of sodium. And because the magnesium cores have twice the positive charge, the electrons are attracted more strongly to them. As a result, magnesium has stronger metallic bonds. Another factor affecting the strength of metallic bonds is how the atoms pack together in the lattice. Sodium atoms pack together in such a way that each atom is in contact with 8 other atoms. Magnesium atoms pack together in a tighter geometry, each atom in contact with 12 other atoms, giving magnesium metal a higher atomic density than sodium. The higher density of atoms in magnesium means that it has stronger metallic bonding than sodium. The combination of a denser sea of electrons and the closer packing of magnesium atoms results in a higher observed melting point of magnesium metal. So, in this video we've explored the bonding between metal atoms, seeing how the free electrons in the structure are attracted to the positive nuclei. We've also seen why the strength of this bonding varies in different metals. In other videos, we'll show how this bonding explains the properties of metals, like malleability, ductility, and conductivity.
Okay, so I think that video actually does a great job of kind of recapping the whole process of metallic bonding. It also dove a little bit deeper into kind of understanding how the bond strengths between different metal types can vary. You do not need to know or tell me which type of metal would be stronger than which, depending on how many valence electrons they have. You do not need to do that. But I like to show that because when I say things like there's variable strengths depending on the type of metal, that kind of maybe makes it make a little bit more sense in your brain. Y'all probably also saw in the video, you're like, well, sodium only melts at 98 degrees. Yeah, that's 98 degrees Celsius though. 98 degrees Celsius is basically the temperature at which water would boil at. So even my weakest metal bond type is gonna be still pretty high. So collectively, if I were to take an average of all of the possible melting points of metallic bonding, they would still be the lowest, which puts metallic bonding my weakest out of my 3 bond types. So it's metallic, ionic, and covalent. Okay, my last topic that we're gonna go over is alloys. So very few metals, you guys, that you encounter in your everyday lives are pure metals. That means very few of them are made up of only one thing from the periodic table. Well, what's the reason for that? Well, most metals are called alloys. An alloy is a mixture of 2 or more elements, which at least one is a metal. Okay, so here's some examples. You've probably heard of brass before. Brass is actually an alloy of 2 different metals, copper and zinc. Okay, sterling silver is another one. It's made up of silver, mostly silver, and copper. That's what makes up sterling silver. Stainless steel, a lot of our stuff is made up of stainless steel. That's an alloy of iron, chromium, and a little bit of nickel, and a little bit of carbon. You're like, carbon is not a metal at all. Yeah, but by definition, an alloy is a mixture of 2 or more things, and you have to have at least one of them be a metal. So there can be some non-metal things in there. As long as there's only one metal representative, you're an alloy. Okay, you do not need to know or memorize any of these specific types. I thought I would give examples that kind of highlight what the differences are and show you how different components of different elements can come together to make an alloy. Another key thing that's important here is it's a mixture, which means all of these guys are not bonded together, okay? Copper and zinc did not attach to each other and now be like, we're copper zinc oxide or something. No, they're just hanging out around each other, which means if I wanted to, I could separate all of these elements from each other through physical means by like melting things, right? Okay, so why do we make alloys? Y'all, alloys are super important because their properties are often superior to those of the component pure element parts. Okay, sterling silver is actually harder and more durable than pure silver, but it's still soft enough to be able to make jewelry and tableware. There is a reason why we do not have jewelry that is just pure silver. Y'all, it would be way too soft and it would not work. Sterling silver is more durable, less resistant to corrosion and other weird stuff like that. So it's got superior properties than just plain old silver. Brass is harder and it's easier to shape than either copper and zinc are separately. So that's why we use brass, like stainless steel, you guys. So we're looking at these alloys actually bringing a lot more to the table than any one of these pure elements could on their own. Okay, so I think that that's our lesson on metallic bonding. Once again, metallic bonding, delocalized electrons to make positive metal cations in that sea of electrons. We're very excited to now move on to the next type of bond, which is ionic bonding. So y'all get ready for that.